All right, hello everyone. Today we've got our Chapter 3 lesson. Prior to this, we talked about in Chapter 2 categorical data, how to display that, how to summarize it. Today we're going to do the same thing except with quantitative data. As a quick refresher, quantitative data by definition is something or data that makes sense to take the average of. So if we took the average of everyone's student ID number, that wouldn't really tell us a whole lot, would it? Whereas here we have the magnitude of different earthquakes, and we could take the average of that to find what the average magnitude was for this set of earthquakes. So a histogram, most of us have seen these before. They are often mistaken with a bar graph, but histograms are what we use for quantitative data. So a histogram is a great display for showing the distribution of quantitative data. We will not have to make these by hand. I'm going to show you in class how to make these on your calculator. But each of these small bars are what we call bins. So we start with our range of data. In this case, we go from 4 up to about 9.2, I would say. And then we want to make sure that our bins are of equal width. So here we're about 0.2. So we go from 6 to 6.2, 6.4, and so on. So there's the advantage of using histograms is that the whole distribution is easy to see at a glance. Just by looking at a histogram, we can tell that most of our earthquakes are right around that 7 to 7.2 magnitude. The disadvantage, though, is that we are not able to see what the individual magnitudes for these earthquakes might be. So for example, if we look in this big bin from 7 to 7.2, we don't know if all of those earthquakes were around 7, if all of them were around 7.2, or if they were kind of spread out in the middle, okay? So an advantage of this, we can see the whole data set very clearly, general patterns, but we are not able to see individual pieces of data. Another type of quantitative display we have is a stem and leaf plot. Stem and leaf plots, they show the distribution of a quantitative variable just like histograms do, while preserving the individual values. So like I said, with the histogram, you were not able to pick out the individual data pieces, whereas in a stem and leaf plot, we can see exactly what each individual data piece is. So one really important thing when it comes to a stem and leaf plot is that you always want to have a key. So maybe in this stem and leaf plot, we have test scores on the most recent AP Stats test. Well, it says here in our key, 5 bar 6 is equal to 56%. So that means in this class we had 56%, 67, 67, and so on. So you can, like I said, individually pick out each one. So if you were to turn this sideways, so turn it 90 degrees to the left, you would still be able to see the general shape of our stem and leaf plot or of our distribution. We would see that most people are in that 70 to 88% range. So as an example, we have a histogram and a stem and leaf plot of the exact same set of data. So we have resting heart rate for 24 women at a health clinic. Think about which one you prefer. There's not really a right or a wrong answer, but which one do you think is more useful for this 24 women in this data set? I guess for me personally, if there's a smaller data set, I think it's useful to use the stem and leaf plot. That way you can pick out individual data values. Whereas if we have a larger set of data, the histogram might be more useful because I don't really want to write out every single data value if we have like 200 or 300 pieces of data. So let's look at this example of how to create a stem and leaf plot. Now, histograms you'll not have to make by hand, but stem and leaf plots, because they're used for smaller data sets, you may have to. So the first thing you want to do if we're looking at worst test grade that you've ever gotten on a math test, you first want to start by cutting each data value into leading digits, which we call stems, and trailing digits, which we call leaves. So this means if you got a 20% on a test, the stem would be the 2 or the 20 portion, and then the leaf would be the digit that comes after that. So then you want to use the stems to label our bins. So as you can see here, I have a stem column 0 through 8. That's 0% up to the 80%. Then we want to use only one digit for each leaf. Now in a moment here, you're going to create an example where we have double-digit stems, and you're going to see the importance of why you want to have only one number as each leaf. And then, of course, in addition to the title, you want to have a key. So why don't you guys try this one out? I want you to construct a stem and leaf plot for the following set of data. And here we have the weights of patients at a pediatric clinic. So pause the video, take a moment, and try this out. All right, so hopefully you took some time to try making this on your own. So again, we've got our data set, and I've got my correct stem and leaf plot on the right here. I want you to note a couple of things. So first off, the key is very important. So over here, I have 4 bar 4 stands for I have percent. Sorry about that. It should be 44 pounds, right? Not percent. Okay. I also want to note one really important thing that people sometimes forget is that in the 30s, we had no kids who were in the 30-pound range. So instead of skipping over that, going from the 20 to 40, you still want to include that 30, but just keep it empty, okay? With quantitative data, if we have a gap in our graph, that's meaningful. That means that we have nothing from 30 to 39, and we want to make that clear. And then, of course, you want to make sure that you have spacing. So here in the first stem, we have 20 and then a space indicating that the next data value is 23, okay? Last thing I'll point out is if you look towards the bottom where the stems are 10 and 11, the issue here that some people have had in the past is that instead of 10 and 5 to indicate 105 pounds, what they'll do is they'll do 1 as the stem, then do 0.5 as the leaf, okay? The reason you can't do that though is because if you have 1 as a stem and 0.5 as a leaf, that's going to look like two separate data values. It's going to look like 10 pounds, then it's going to look like 15 pounds, okay? So before, when I said your leaf should only be 1 digit, that's exactly why. Now, I had showed you earlier about dot plots. So here's an example of a dot plot. A dot plot places a dot along an axis for each case in the data. So in this case, we have a dot plot of the winning Kentucky Derby times for the past 100 races of the Kentucky Derby. You might see a dot plot displayed horizontally or vertically. So here we actually have our scale on our y-axis, and then we have our frequency on the x-axis. You could rotate that if you wanted, it would still give you that shape. Now, one really interesting thing about this particular data set is that we have a lot of data values from like the 118 to 135 range. And then we have also another set from 154 up to about 165. So I want you to take just a moment here. Think about what might cause that gap. Why are there no times in that 135 to 152 range? Think about that just for a moment. So typically we'll have this discussion in class, but hopefully you took some time to think about that. One really primary role or key thing that will determine the winning Kentucky Derby time is the weather, right? So if it's nice and dry out, no rain on that day, typically the ground's going to be a lot more solid. So that's probably where these faster times came in, all those below 135. Whereas if it were raining, that's going to cause some mud. It's on a dirt surface, so if it's wet, it's going to turn muddy, and that's likely where these slower times came from. When it comes to quantitative data displays, one of the most important things that we could do is describe the distribution, okay? And that's really going to be our primary focus of this unit. Of course, we want to be able to read and maybe create some of these graphs, but describing the distributions is what's most important. So take a moment. I want to know, how would you describe in the most detail possible this distribution? Take a moment and think about that. So I'm not sure how you describe that distribution, but from here on out, when I ask you to describe a distribution, you have to address 4 main things, and we'll talk about each of these individually. We have to talk about shape, center, outliers, and spread, okay? One really easy way to remember that is through SOX, okay? We're missing the K, but shape, outlier, center, spread. So if I ask you to describe a distribution, you have to talk about all 4 of those things. So when you're asked about the shape of a distribution, we want to answer these questions. Does the histogram have a single central hump, or does it have several separated humps? We also want to know, is the histogram symmetric or is it skewed? And finally, are there any unusual features that stick out? So when it comes to humps in our graph, we want to know, does the histogram have a single central hump or does it have several separated humps? When it comes to statistics and describing a distribution, humps on a histogram are called modes. So if you think of back in elementary school when you found the mode, that was the number that occurred most often, right? So if you talked about test scores, if 10 people got an 80%, odds are that that would be the mode of your class, okay? So a histogram that has one main peak is called a unimodal graph. Histograms with two peaks are called bimodal, and anything 3 and higher for number of modes is just called multimodal. So this has two humps. We have one right around 85, one right around 125, I'll say. So this would be considered bimodal. Now, it's not always the case where a graph will have a very clear mode. So a histogram that doesn't appear to have any mode at all, and in which the bars are approximately the same height, is called uniform. So if we look at this, this is the expected value of rolling a six-sided die 100 times. There are some bars that are higher than others, but for the most part, it's pretty flat across the top. That's why we call it uniform. So try not to mix up the words unimodal and uniform. Unimodal, again, that's where we have one very clear hump in our graph, whereas uniform means we have a level top. Another aspect of shape when you're talking about a distribution is we want to know, is the histogram symmetric or not? So I think most of us are familiar with the term symmetric. Essentially, if you cut a graph down the middle and you fold it over onto itself and it's roughly matching up on each side, that's what we call symmetric. Now, very seldom is a graph perfectly symmetric, so we want to use non-deterministic language such as roughly or approximately. In this case, we could say this graph is roughly symmetric. Now, kind of the opposite of being symmetric is if our graph is skewed. So the thinner ends of a distribution are called tails. So if one tail stretches out farther than the other, the histogram is said to be skewed to the side of the longer tail. So if we look at this blue graph, here we have the number of female cardiac patients for each age category. The tail is on the left side, so we could say this distribution is skewed to the left. It's unimodal, but it's skewed to the left. In purple here, if we look on the right side, the tail goes off to the right. So this would be an example of a skewed right distribution. So after shape, in SOX, we want to talk about O, which stands for outliers. Most of us know or have heard of what an outlier is in the past, but you should always mention any stragglers or outliers that are far away from the majority of your data in a distribution. Another way to acknowledge outliers is that you can just point out gaps. So if most of your data is around an 80%, but one person got a 10%, you could just acknowledge that gap in your graph, or you could actually point out that specific outlier. So I actually contacted one of my old NDSU professors, great guy, wonderful teacher, but the content is super difficult in his class. This was a test score distribution for a recent abstract algebra test. When I say abstract algebra, I mean it's an algebra where 1 + 1 is no longer 2. It's just really wild stuff. So in this distribution, it seems that for the most part, people got in that 50 to 60% range, which unfortunately was pretty typical when I was taking the class. But then we have a low outlier in that 1 to 10 range, okay? So when you were describing this in terms of shape, we could say it is roughly symmetric, it's unimodal. And in terms of outliers, we would say there is one apparent outlier in the 1 to 10% range. So we've talked about shape, we've talked about outliers. Now in SOX is C, we're going to talk about the center of a distribution, okay? So just for a moment here, I want you to answer this question. If you had to pick a single number to describe all the data in a data set, what value would you pick? So for example, if we're talking about income of all staff members at Fargo North High School, what single number would you choose to represent all people in that data set? Well, it's easy to find the center when a histogram is unimodal and symmetric, right? It's just in the middle of our graph. But on the other hand, it's not so easy to find the center if we have a skewed histogram or a histogram has more than one mode. So to answer the question of should we use the median or the mean to describe our center, let's take a look at this example. Here we have the number of text messages sent by a group of students in 1 week. On the low end, we have 2 text messages, and on the high end, we have 75 text messages, okay? So think just for a moment here, would you pick the median or the mean to represent the center of our data? So you might have different opinions. I know that in this example, the median and the mean aren't too far away from each other, but in general, if we look at this, most of our data is in that 20 to 27 range. But if we were to take the mean of this data, that 75 is going to pull our mean up, right? So when it comes to finding the average or finding the mean, if we add bigger numbers into our calculation, that's going to raise our mean up, okay? Whereas if we find the median, that's where in elementary school or middle school, you cross off the low number, then the high number, low, high, until you found the middle. We're actually going to disregard that 75 when we find the median. So if it's the case that you have a skewed distribution or you have an extreme outlier, as we do here, then you want to report the median. We say that the median is resistant to outliers because we kind of disregard that outlier when we're calculating the median. On the other hand, in this graph, we don't have any apparent outliers. We also do not have any skewness to the left or to the right. So in this case, the mean would be most representative because the mean is going to be right in the center of our data set. So now we've talked about shape, we've talked about outliers, and we've talked about center. The last thing we have to address when we talk about a distribution is the spread of the data. So as I said in the first week of school, statistics is all about variation. We want to know, are the values in our distribution tightly clustered around the center of our distribution, or are they more spread out? So in addition to talking about the center, we want to talk about the spread of our distribution. So one way that we can measure spread is through the use of the range. The range is simply the difference between the maximum and the minimum values in our data set, okay? So if we're talking about test scores in a abstract algebra class, let's say the highest score was 100%, lowest score was 5%, we would just take 100 minus 5, meaning that our range is 95%. What I want you to think about is what is a disadvantage of using the range? Think about that for a moment. Well, maybe to answer this question, we can think about the example of if we randomly select 20 Fargo Public Schools employees, let's say that 19 of them are either support staff like paras, janitors, or maybe they're teachers, and then one of them is Dr. Gandhi, our superintendent. Well, if we were to find the range of that data set, we would take Dr. Gandhi's salary, which is around 220,000, and then if we take the low end, maybe that's around 30,000, that's going to be a really significant range. So does that really represent the entire range of all employees in the district? Probably not, because most people are not making as much money as Dr. Gandhi is. So a disadvantage of the range is that if you have a low outlier or a high outlier, it's going to make it seem like your spread is a lot greater than it truly is. So one way to disregard some of the extreme data values that are on the low end or on the high end, we can find something called the interquartile range, which is also abbreviated as the IQR. IQR in short is the middle 50% of our data. So we're going to ignore the bottom 25% and we're going to ignore the top 25%. So in order to find what our interquartile range is, we first have to divide our data into what's called quartiles. So quartiles divide the data into 4 equal sections. 1/4 of the data lies below the lower quartile, which we call Q1. Then 1/4 of the data lies above quartile 3, which is called Q3. And the quartiles border the middle half of our data. So within that range from Q1 to Q3, we call that our IQR. So the difference between the quartiles, if we take the upper quartile, which is Q3, minus the lower quartile, which is Q1, that is what we call our IQR, or interquartile range. So in this distribution of magnitudes of earthquakes again, we see that we have some pretty low extreme outliers. So if we were to find the range, that would be 9.2 minus about 3.6, which is a pretty significant spread just using our range. So by doing the IQR, or the interquartile range, we again disregard those lower extreme values, and instead we find our middle 50% of data. Okay, so here in our 5-number summary in the table here, we have a Q1 of 6.7 and a Q3 of 7.6. And that's what's shaded in yellow, or this tan color in the graph. So that means our IQR, if we take 7.6 minus 6.7, Q3 minus Q1, our IQR is 0.9. So speaking of that 5-number summary that we saw before, that's made up of our minimum value, our quartile 1 or Q1, our median, Q3 or quartile 3, and our maximum. Then we can create what's called a box plot, and a box plot is just a graphical display of our 5-number summary. And box plots are useful when comparing groups and finding outliers. So in this case, if we look at company A, we see that the lowest number of stocks sold is 1,000. Then the 25% cutoff for that, or the Q1, is around 1,500, just a little bit below 1,500. Then this red region shows our second 25% of data. So we go from 1,500 just about to 2,600. And then this green section is our third quarter of our data. This is 2,700 or 2,600 up to about 3,500. And then our top 25% are 3,500 up to about 5,400. Okay. So in this case, our IQR is 3,500 minus 1,500. Whereas if we were finding the range, that would be our maximum value of 5,400 minus about 900. So my hope is that I didn't completely flop and forget to show you how to make a box plot before you are watching this video. So if I did forget, I apologize. I'll show you how to make a box plot later on. But what I'd like you to do, try to create a box plot. What I've got here, this is actually real data from my apartment building. I can pull this off because I manage my apartment building. But what I did, I just asked people in my building if they were willing to share their ages, and these are the people that responded, okay? So I didn't include myself, but I have nearly all of the people in my building share what their ages were. So what I'd like you to do is construct a box plot of this data, and pause the video and I'll show you what it should look like. So let's go ahead and take a look at how you would make a box plot of this data. I have added 30 animations to this, so hopefully they all come in order. Well, the first thing you want to do, if you look at your data set, make a reasonable scale for your data, okay? So we see that ages are ranging from 22 to 95. Remember, we want our scale to go up by a consistent amount. So here, 10 is a pretty good bet. That's a really easy number to work with. So we go from 0 up to 100. Okay. Then what you want to do is start by finding your 5-number summary. So you've got your scale. For the 5-number summary, the two easiest ones to find are the minimum. In this case, 22 is our youngest age, and our maximum is 95. Then after you find your minimum and maximum, we have to find the median, okay? So this is where we go back to what you probably talked about in elementary school, where you do the low, the high, low, high, and you continue this pattern until you get to the middle of your data. In this case, your median is between the ages 69 and 80. So remember, if your median lies between two values, this is where you have to add them up. So 69 plus 80 divided by 2, That gives us a median of 74.5. Then we have our minimum, our maximum median. We then have to find our Q1. So Q1, you can think of that as the median between the minimum and our entire median, okay? So between 22 and 74.5, we want to find our median. That would give us our Q1. So again, we're only going to look at our first half of our data set. We'll do a low, a high, low, high, and continue that. And if we do this, we actually don't fall between two numbers. We're going to be right at 31. Okay, so our Q1 in this case is 31. And because I didn't want to add 40 animations to this, you would do the same thing for Q3. So you'd start at 80, cross it off, 95, 80, 94, 80, 91. If you continue that, you'll see that the Q3 is 86. So that gives us our 5-number summary. Okay. Now, if we knew for sure, like they stated, there are no outliers, then we could just plot our box plot here, okay? It would be made up of, the box would be 31, 74.5, and 86. Then we'd have our whiskers going from 22 and then to 95. But I'm going to require you from here on out to check for outliers. So let's do that. The first step when checking for outliers, you want to find your IQR. So remember, that's Q3 minus Q1. In this case, 86 minus 31, which is 55. Then a constant, this is the same thing every time. We're going to multiply our IQR by 1.5. So 1.5 times our IQR, that's 1.5 times 55 is 82.5. This 82.5 tells us how far above or how far below our majority of our data we want to be before we consider a point an outlier. So let me show you how that works. So for high outliers, what you do, you take your Q3 plus that 1.5 times the IQR. So in this case, that's 86 plus that 82.5 we found, and that gives us 168.5. Well, because there is no person in our data set that's older than 168.5, that would indicate that we have no high outliers. So in this data set, no high outliers, so we don't have to put any stars or points on our graph. Then we do the same thing for low outliers. So for low outliers, instead of starting at Q3, we start at Q1, and then we subtract this 1.5 times the IQR. So in this case, Q1 is 31, 1.5 times the IQR is 82.5, and that gives us a lower cutoff value of negative 51.5. Well, clearly nobody is younger than negative 51.5. That doesn't even make sense. So again, that would indicate that there are no low outliers, okay? So in this case, there are no outliers at all on the high or the low end, so we don't have to put any points on the plot. So finally, going to our graph, this is what our box plot would look like. You'll see that the middle line or the center line of our box is right at our median of 74.5. The lower end of our box is exactly where Q1 is, that's 31. The higher part of our box is at 86, that's our Q3. Then our upper whisker extends to our maximum, which is 95, and our lower whisker extends down to 22, which is our minimum value. So I thought maybe I'd show you how a histogram and a box plot compare. Again, both of these are really great for summarizing data. There are some pros and some cons to each one. So in the histogram, we are able to see that it is a unimodal distribution, and we can see that most of our data is in that 6 to 8 magnitude range, okay? For our box plot, we can see something similar to that. So remember, each quartile of our box and whisker plot is 25% of our data. So if we look at the box portion of our box and whisker plot, that's a really condensed, kind of a crunched space, okay? So that means 50% of our data is in a really, really small range, about 6.8 up to about 7.8, okay? So that would indicate that the middle 50% of our data is not very spread out, okay? Now in the histogram, you might be thinking, well, those points to the left look like they might be outliers, but we can't say for sure when it comes to a histogram. That's another benefit of a box plot. We see that these points here actually indicate that those points are outliers, okay? And I wouldn't have guessed in the histogram that on the right we have any outliers, But again, looking at our box plot, we have 2 outliers on the high end. Okay, so one note on the mean or the average, we're going to refer to it as the mean from here on out. The mean feels like the center of our data because it's the point where the histogram balances, okay? So that means when it comes to finding the mean, we're going to add up all of our data values, then divide by the number of data values that we have, okay? So on the right here, that's what that equation means. So that total is going to be the sum of all of our data values, and we're going to divide by the number of data values we have. In sigma notation, that sigma symbol means sum, so sum them up. Sum up all of our data values y and divide by the number of data values. Now, one final measure of spread, and this is the one that we prefer to use, is called the standard deviation, okay? IQR is really great, but it does have some limitations. If you think about the IQR, really all it does, it's similar to the median. It's kind of a snapshot of just a handful of points. The standard deviation, on the other hand, takes into account all of our data values. So by definition, standard deviation is the distance on average you can expect a randomly selected data value to be from the mean. So if we think about our classroom example, if we wanted to know the standard deviation of the heights at Fargo North, well, let's say that the average height is 65 inches and our standard deviation is 3 inches, okay? What that would mean is that on average, if we select anyone at random from Fargo North, we would expect them to be within 3 inches of our average, which is 65 inches. Now, don't worry too much about calculating standard deviation by hand. Our calculator will do that for us. But what you need to know is that variance is what we start with, okay? So variance, that is notated with S squared. That's how we start by finding our standard deviation. Then find standard deviation from variance, we just take the square root of that. So my plan is that in class, we're going to do a little more investigating with standard deviation, and I'll show you how to actually calculate this by hand. So that's essentially what you need to know. I have to apologize for the length of this video, but there's a lot of good information in here. We will apply and practice this in class, but what I'd encourage you to do, take a look at your notes, try some of the Chapter 3 homework problems, and we can answer any questions you have when you get back to class.